Welcome to my innovation project video. Space organizations will start sending ships to colonize other planets. What was unlikely just a few decades ago is now likely to happen sooner than we expected. The colonization of other planets will be good for reasons like more housing being provided and more resources being available. Whether you just want to live on another planet or because you think this means a bright future for humanity, colonization is quite exciting. As I researched the subject, I found problems related to colonization. The designs of current ships not being suited for the task of colonization was the most apparent. For colonization, spaceships should be designed to carry as much as possible with the least amount of weight, while being able to withstand obstacles of interplanetary travel. The geometry of the spaceship has a direct impact on its ability to fulfill these objectives. To make this spacecraft's shape as efficient as possible, 3 variables must be considered: resistance, volume, and aerodynamics. Research shows that the shape with the best surface area volume ratio is the sphere, the most aerodynamic shape is the teardrop, and the most resistant shapes are the arc and the triangle. The most effective design should combine the advantages of these 3 shapes. My research question is, what is the most efficient shape for a spacecraft built for colonization? My hypothesis is the most effective shape for colonization spacecraft is an egg shape because it resembles an elongated sphere, which optimizes volume. It resembles a wider teardrop, which gives it aerodynamic properties, and it has a conical top, which gives it a resistance similar to that of a triangle or an arc. My independent variable is the shape of the ship. It will change between egg-shaped, sphere-shaped, and tetrahedral-shaped. My dependent variable is the efficiency tests, and they will be tested to see which is the most aerodynamic, voluminous, and resistant. My control variables are the model's material, plastic, the model's size, they will be the same height and length, and the medium. In the first test, they will be all tested in the pool. The materials I will use are a 3D printer, a computer, a pool, a fishing line, an RC car, 3 tetrahedron models, 3 sphere models, 3 egg models, lead sinkers of different weights, a tall cup, a medicine dispenser, a scale, a pair of tweezers, tap water, a C-clamp, a knife, a pen, and a stopwatch. Experimentation. Design. Design an egg, a sphere, and a tetrahedron on a computer using Tinkercad. Aerodynamics test. Use the scale to weigh each model. Record their weight. Add sinkers to each model to submerge them in the water so that they can be properly tested. Make sure that the combined weight of the model and sinkers is the same for every test, which ensures that the only variable that changes in this experiment is the model's shape. Tie one end of a fishing line to the model and tie the other to an RC car. Start a stopwatch when the car is started and the model is at one end of the pool, and stop it when it reaches the other end. Record the time. Repeat this 3 times. If the 3 results are close and consistent, the result that is obtained is most likely correct. If they are not, increase the sample size. Volume. Use a tall cup, medicine dispenser, and clippers. Use the same materials and equipment to test each model to make sure only the shape variable changes. Fill the cup to 2/3 with water and mark the level with a pen. Use the clippers to submerge the models into the cup completely and the water will rise. Mark the level the water rose to. Repeat this 2 more times to ensure that the water level rises to the same level every time. Doing this 3 times with consistency proves confidence to the sample size. Remove the model, make sure the water is at its original level, and use a medicine dispenser to put water into the cup until the mark is reached. Record the milliliters of water needed to reach the mark. Using the weight of the shape previously recorded and recorded milliliters, calculate the volume to weight ratio. Resistance. Adjust the C-clamp to each model and turn it until the shape breaks or deforms. To make sure that the shape of the model was the only variable, the same person was turning the C-clamp using the same force. Since the test destroys the model, there will be a limited sample size. Record the number of turns it took to break the model. Analysis. Aerodynamics. This test was done to find out which shapes are the most aerodynamic by pulling a model through a pool with an RC car. This test results are: the egg-shape average time was 13.8 seconds with a range of 0.6. The spheres was 15.2 seconds with a range of 0.2 seconds. The tetrahedron was 16.9 seconds with a range of 0.1 seconds. The egg-shaped model's time was the shortest, and it did the best in this test. Volume. This test was to find which shape has the best ratio of weight to volume by using volume displacement. This test results are: The egg shape's weight to volume ratio was 2.5, the sphere's was 3.5, and the tetrahedron was 2.5. This data says that the sphere shape has the best volume to weight ratio, and the egg and tetrahedron have the same. Therefore, the sphere did the best in this test. Resistance. This test was to compare the resistance of the shapes by adjusting and turning a C-clamp to compress the model until it breaks. This test results were: the number of turns that the C-clamp took to break the egg shape is unknown, as it couldn't be turned past 2.5 turns. The number of turns it took to break the sphere was 2, and the amount it took to break the tetrahedron was 5. This data means that the egg withstood the most and it did not break. Therefore, the egg shape did the best in this test. The egg did best in 2 of the tests and did as expected in the third. The sphere did best in the volume test and did as expected in the other 2. The tetrahedron did not have the best results in any of the 3 tests. In the aerodynamics test, there was a difference across the 3 models. In the volume test, there was a difference between the sphere and the other 2 models, but the other 2 had the same volume to weight ratio. Finally, in the resistance test, there was a large difference among the models, one of them not being able to be broken at all. This graph's data says that the egg shape was the fastest and thus the most aerodynamic because it took the less time to cross the pool. This graph's data shows that the sphere has the best volume to weight ratio because its ratio is the highest. This graph's data shows that the egg's resistance is best because it couldn't be broken. The graph shows no data for the egg as it couldn't be broken and the C-clamp could not be turned past 2.5 turns. It was hypothesized that the egg would do the best overall when comparing the 3 shapes because it has aerodynamic properties similar to the most aerodynamic shape. It resembles the shape with the best volume to weight ratio, and its conical top gives it resistance similar to the most resistant shapes. The results that proved the validity of my hypothesis were: in the aerodynamics test, the egg was the fastest with an average time of 13.8 seconds. In the volume test, the sphere had optimized volume with a volume-weight ratio of 3.5, and the tetrahedron and the egg tied with a ratio of 2.5. And in the resistance test, the egg could not be broken. Since the egg did the best in 2 of the tests and did well on the remaining one, it did the best overall. The best shape for a colonization and transportation spacecraft is an egg shape. Therefore, whenever a colonization spacecraft should be designed in the future, an egg shape is the best choice, as it is resistant, it does well optimizing volume, and it is aerodynamic. All of the tests went well, but some challenges were faced. One challenge was the different weights of the models and the fact that the models floated. This was resolved by using sinkers that submerged the models, which was needed to test the model's drag. The research question was answered because the tests helped to clearly identify the best shape for a colonization spacecraft. These tests were fair and valid because the experiments were conducted to find the best shape for each criteria without bias. The reliability of the aerodynamics test could have been improved by not relying on a person to start or stop the stopwatch. Instead, this could have been done electronically. Wind tunnels can also measure aerodynamics more accurately than pulling a model through a pool. One limitation was a lack of 3D design skills. How it limited my experiment is I couldn't do the tests as they were originally planned. A solution to this would be to spend more time learning how to design the models. Another limitation was a lack of a way to measure milliliters exactly. The medicine dispenser only had 2.5 milliliter increments, and a solution to this was to get a more accurate instrument to measure milliliters. A third limitation was a lack of an instrument to properly measure strength or resistance. The C-clamp couldn't be turned more than 2.5 times during the egg's resistance test, and the solution to this was use an instrument that accurately measures the resistance of models. Thank you so much for watching.